We're going to finish our data security on the last part of cryptography by talking a bit about or mentioning a couple of systems that are trustworthy, so to speak. And then we're going to talk about stream and block ciphers. And then mention public key or shared key encryptions. Now, first, trustworthy encryption systems. When we say that they're commercially great or trustworthy, we mean that it meets these criteria. So the mathematics behind it is sound or has been proven. It has been analyzed and tested by competent experts, and it has stood the test of time. So it hasn't been cracked. Three algorithms are popular today that meet the above criteria, and I'll put in some links for you to have a look at if you want to know more about them. I won't go into detail about each of these, but they are good standard algorithms that have stood the test of time. Now, I talked about two different types of encryption algorithms. There are two types of ciphers as well, so stream and block ciphers. The substitution ciphers are stream ciphers. That is, they convert a single symbol at a time. So that they for each symbol they convert that symbol or character into something else, and just keep on going. So as like a stream. The transformation only depends on the symbol, the key, and the control information of the algorithm. So, for example, you could skip a character in the key during encryption, and it affects all future characters. So that's what I mean about control information of the algorithm. Block ciphers are encrypt a group of plain text symbols. So columnar transposition is a block cipher. It treats the entire message as one block when it's translating it. So block ciphers work on blocks of plain text and produce blocks of ciphertext. So it's not like before. It's not the stream. It depends on, it takes the whole message, puts it into blocks, and then transforms it. Now, like I said, two types of encryption algorithms, symmetric and asymmetric. And we've gone through this before. But we're going to now, but we've mostly been focusing on the symmetric ones, where we have one key for Caesar ciphers, we have one key for blocks and stuff like that. What we're now going to talk about is asymmetric, where encryption and decryption keys come in pairs. So, because that is the standard for public key encryptions. So where each user has two keys. You have a public key and a private key. The user may publish the public key freely, and the keys operate as an inverse. So one key undoes the encryption provided by the other. For example, so the example is, or we denote the private key of a user by kpriv, and kpub is the corresponding public key. And we can write the relationship as that the plain text is the decoding with the private key of the encoding of the public key of the plain text, and vice versa. So the decoding of the encoding with the private key and the public key. So you see, here we have the private key and public key, but the other one is public key and private key. So that is the relationship of it. So I'm going to explain the main motivation for the development of asymmetric encryption systems. So take the symmetric key, for example. As the number of users grow, so for each new user that comes into the system or into that communication network, they have to make n times n minus 1 divided by 2 keys for each user. So each user has to connect with each and every other user, and they have to have a set of keys each. And it's harder to maintain security if the keys already distributed, and we can't expect users to memorize every single key that they have. So Diffie and Hellman proposed an asymmetric or public key encryption in 1976. And in that system, with a public key, just one public key, anyone using a single public key can send a secret message to a user. So every existing user only has to have their single private key, while the shared key is shared between everyone else. Now, public key algorithms are useful for specialized tasks. They are slower than symmetric keys, because you can think about if you're transforming twice with asymmetric keys, and you have to make computationally heavy calculations for each. Like they're 10,000 times as long to perform than a symmetric encryption, and they're of course slower than the bit operations. Now, symmetric encryption is therefore the cryptographer's workhorse, and public key encryption is reserved for specialized infrequent uses. Now, the beautiful thing about this is that you can combine symmetric and asymmetric encryptions to get the best features of each. So you can use asymmetric encryption to send the or share the symmetric key for something else. So you can use like asymmetric for key exchange and digital signatures. You can use symmetric to decode and encode the from databases or something like that. But the use of encryption doesn't solve all data security needs. You have to have a whole system in place. So it's a crypto system, and you have the whole security of the software system as well. Now, let's talk a bit about the highlighted thing there, key exchange. So let's say you need to send a protected message to someone you don't know and who doesn't know you. So for example, if you're sending an income tax return to government, a web browser to connect to shopping sites, encrypted emails, for example. Now, you would want to have a symmetric encryption of that because that's quicker for something big. Now, but how to exchange symmetric keys, securing that nobody intercepts them? The problem is almost circular. So it's a problem of the hen or the egg, which came first. To establish an encrypted session, you need an encrypted means to exchange keys. There, the public key cryptography can help. So it's a kind of, but how do you share the symmetric key? So let's say Alice and Bob want to start an encrypted session between them. So they both know the public key. They have their own secret colors, which no one knows but them. They blend their colors with the common paint and send that key over to each other. So they are not sharing their private keys. They're just sharing a common. They're sharing their mix of the public key with their private keys. So there's really expensive to mix or separate the mixture to get their keys. Really expensive. We assume so, but they now have what each other has. Then, if they mix again with their private key, they get a common secret that nobody knows except them. So that's the symmetric key then, that they only know but nobody else. Only thing that was transported between them that somebody could have intercepted is something that has no meaning for anybody else unless they have both secret private keys. So what this ends up being is the mix of this. So each of this is a mix of the public key and each private key, and nobody knows the actual private key, but it's a mix of these three colors. So these three colors. Doesn't matter in what order you mix them. In this order or that order, you will get the same end results. But the end results wasn't exposed to any public transport. Only the intermediate results.